not accepted.
All right. Hello, beautiful audience. I'm glad to be here today in this amazing city, marvelous conference, and today is a good time to talk about big data. Before we get started, let me introduce myself. I'm Boris Trofimov, and I'm Big Data Competence Lead and Architect at Sigma Software. We are Ukrainian, Swedish, or Swedish-Ukrainian software development company. My primary expertise is big data and high-load systems, and particularly I built a data platform for Verizon Media, LOL data platform with incoming rate 2.5 million events per second. And today we've been talking about big data trends in big data. And I split our discussion into four topics. And the first topic is about big data visibility and the fact that it's getting more tangible outside big data boundaries. And this is kind of intro for those folks who are not familiar with big data as well. So sometimes big managers think that big data is a magic spice, something that if you add to your project, you'll immediately succeed. And it's like magic wings, and it would elevate your product into the next level. The reality is a bit different. And sometimes these projects might fail because of different reasons, plenty of reasons. But sometimes it's a lack of specific knowledge, specific practices, which big data means. And we'll be talking about it today. Let's find out a place where big data lives on typical solution. So, very often big data is about data analytics. And if we address typical solutions, then we have front end as a component, we have back end as a component, and very likely we will have a component which will work with data. What it means usually, we have ingestion, we take data, we're pulling data, we're transforming, enriching, validating, doing some magic, and then we expose data. And that component exists, and call of it is data platform. So it's a place where big data lives. And if we open up the hood of the big data and take a look on the internal, we will see this. So at the beginning, there were data sources, plenty of data sources. Then we have ETL tier. It's basically the major computational tier where we have our pipelines, processing pipelines, and every pipeline takes data from data source, doing that magic, ingesting, processing, and storing data to data lake. Data lake here, on the one hand, it's a kind of source of truth, where all organization data might be stored and the first copy of data. At the same time, it serves needs of ETL. And intermediate state of data, like raw data, aggregated data, might be stored first inside data lake. And besides that, we have analytical layer. Actually, a layer where we have data in certain organization form where query languages can be applied and data can be queried quite quickly. So it's a place for low latency queries. And usually we have here data warehouses, and data should flow from data lake to data warehouses. We have reporting API, we have BI, business intelligence. And logically, I separate here the data warehouse and data lake. But in reality, sometimes these technologies might be combined into one product, into one solution. And there are even technologies, data lake houses, which we've been talking today as well about this amazing thing. Besides that, what we have? We have data export and data science. All right, and beside code and technologies, there is something new, completely brand new. Well, not exactly brand new, but at least the focus nowadays has been shifted towards this thing. And that's about data excellence. It's data governance practices, and we will cover it as well. It's a very important trend nowadays. And I would remiss if don't mention some infrastructure activities. Usually this stuff like infrastructure management, scrim tests, security, and so on. This is shared, responsibility shared between engineers, DevOps, and other guys, security, and so on. All right, so you can notice that data platform might be quite complex beastie, and you need a lot of things to make it quite good and solid. And that's why there is a whole expertise called data engineering behind it. And who are those magicians and wizards who know all this stuff. And name of them is data engineers. And there was a touch base between these two worlds, data engineering and the ordinary backend engineering, for instance. Well, trend is quite clear nowadays. Data engineers are getting to play more and more active roles in projects. A lot of companies recognize this expertise and hire data engineers, extend existing teams who are owners of these data platforms. And there is another way to build teams, by the way. A pure dream introduced by Martin Fowler and Jean-Marc Dehany. They call it cross-functional team. These teams should be built not around the technology, but around the subdomain, which is a bit different notion, concept, and it has certain pros and cons, and it's a very interesting approach. But it requires certain rethinking on the way how teams should be composed afterwards. All right, and the last thing here, it's a technology exchange. I'm sure that backend engineers are aware of Kafka, which is a big data thing. Many of backend engineers are aware of Spark, and the same about exchange from backend to big data. A lot of big data engineers adopt backend practices. So this technology exchange is quite mutually not exclusive, but mutually beneficial. So that's a trend today. We are these worlds are colliding and merging together. All right, and let's talk about customers then. I'm sure all customers are the same. All they want cheap solutions, delivered ASAP, and with no trade-off on quality. That's nothing special, just a business, like ordinary life of engineer. And we have a lot of pressure from our customers. And I remember other times. I remember times when engineers, data engineers, had tons of time, spent tons of time, played with 100 technologies, and produced just a little output. Because, it's big data, it's never been cheap, everybody said. So customers accepted back then. But nowadays, these days are gone, and everybody, customers, program managers, engineering managers, product managers, and just engineers are seeking for ways how to ensure delivery quite fast. And if you want something, the reality will respond for sure. And we've been witnesses of two revolutions. The first revolution is cloud. You can see that cloud nowadays is playing a very critical role, and you can build almost everything. You can leverage all things into cloud rails, I would say. And cloud gives us a way to build very reliable, available applications with less runway, with short time to market, and it's very cool. And the second revolution is about subject domain technologies. A lot of companies recognize that there are certain problems, and they can make solutions for these problems, like productize these problems, and automate as much as possible. And we have a lot of them. And the second revolution, which speeds up development as well. And a couple more observations. A lot of engineers adopt certain practices and build architectures which are able to localize changes in source code, in decision architecture itself. And it gives a chance to make deployment easier. The feature development lifecycle is shorter because of that. And at the end, you have cost of change lower, which is a good sign. At the same time, those revolutions definitely make lower maintenance costs in many cases. And maintenance efforts, I would say. Not necessarily it will be reduced monthly bill. Not at all. But at least you'll spend less efforts to support it. And the last one here, it's nowadays it's easier to rotate engineers within teams, data engineering teams. Well, many engineers know Scala. Many engineers like Scala. But much fewer engineers available on the market. And that's the reality we live in. We live in a situation when we need to rotate developers. And we need technologies with certain learning curve. And that's a problem for us to staff these teams. That's why a lot of engineers find Python and even Node.js much more preferable languages than, for instance, Scala. I'm particularly a big fan of Scala, but that's reality. And these engineers try to build data platforms driven by smaller, composable, jobs instead of building, big, highly polymorphic, full of abstractions and metaprogramming Scala and Java applications. That's another reality. All right, next section is about architectures. I'm not sure if everybody is familiar with Lambda architecture, but I will explain in brief. This thing was kind of holy grail for years, and a lot of engineers and companies adopted and implemented it. And at least they thought they implemented Lambda architecture. It's still like certain things that requires understanding how to prepare it. But at least a lot of engineers tried to implement it. And it was good. And to be honest, it has certain advantages even nowadays, the way how it works. So imagine, suppose you have a data source with near real-time events or data coming from, and you organize your processing in two layers. The first layer is speed layer or streaming layer. You accept data in near real time and maybe aggregate it in near real time and put it into specific, like, I wouldn't say tables, it's specific views with short time, TTL, I would say, right? And for instance, you might have retention policy on this data 1 hour or 1 day. And this is a constraint, but because of this constraint, you can build specific decisions and speed up this layer a lot. At the same time, you have batch layer, where you have scheduled jobs running like every hour or every day, consuming the same data. But based on the fact that you can run it more rarely, you can leverage it. And for instance, this batch layer might have more data, historically much more data. And the data consumer, what he should do, he needs to pull data from the speed layer, from batch layer, and compose together to make a consistent data view. It's nothing, that's definitely not rocket science. But the good side is that this architecture it has certain high availability feature. Because, you have separation on all tiers. You have separation on processing layer, you have separation on storage layer, you have separation on infrastructure layer, and sometimes developers make separation on source code layer as well. It's good because if, for instance, batch tier will be down, the speed tier will be running, likely, very likely. And a lot of companies, big companies, prefer this architecture because it's highly available. However, it has certain downsides. So beside downsides, it's a quite big implementation time. Like ETA is much bigger, and moreover, once you have it, you need to spend a lot of money and development efforts to keep it alive and running. And adding new feature means that you need to add something to batch layer and to real-time layer as well. So it's a bit increased because of that. But again, a lot of companies accept it because it has quite high availability. All right, and there is a lot of engineers try to find something else, and there is a response, Kappa architecture, which I would say is a alternative, better alternative to Lambda. It's a bit simplified. Instead of having two layers running in parallel, which might be too excessive, somebody thought, okay, let's chain them. Let's run streaming or speed layer first, and then output of it, make an input for the batch layer. And this architecture, well, the downside is that you have longer latency. Data should come through all stages before they're available for application. But at the end, you have simplified availability. You have less development efforts to keep it running because of less technologies involved. And it might seem that it's less available, but in fact, you have certain ways and technologies how to keep it available as well. Not probably as high available as Lambda could be, but still. So it's quite decent approach, I must say. However, there is another winner, I would say. And another trend is to involve Delta architecture. Delta architecture is a brand new trend which arose a couple of years ago. And in fact, it's adoption of Kappa. It's adoption of Kappa. And the difference here is that it relies on specific technology behind the storage layers. Delta architecture imposes that it should be a data lake house in most cases. Comparing like cup architecture, it doesn't impose engineers to choose specific storage technologies. For instance, you can use MemSQL for real-time data and speed layer, and Vertica, for instance, for batch layer, and keep more data in Vertica historical. And that will be fine. However, you involve more technologies and you have a lot of data hops between them. Delta architecture means that you have less data hops. You introduce single technology which will be serving two needs. It will be able to store data batch streaming as well. Yes, it should be capable technology-wide, but it's feasible. Again, these technologies already exist. And besides that, this technology should be able to store raw data, process data, aggregated data, and so on. And this architecture is getting more and more popular nowadays because data lake houses are getting more popular and unlocked these capabilities. It's really cool. All right, do you like pizza? I'm sure you do. And the good side of pizza is that it is delivered to us in already sliced form, 6 or 8 pieces. And I wish to have domains we work and develop sliceable and splittable in the same way. When we start working on the specific solution, the same problem comes. We need to break down complexity. And we need to break down complexity by splitting domain into subdomains. And that's actually the problem addressed by domain-driven design. And data engineering is not an exception. We have the same challenges and problems, and we have our own response to domain-driven design. It's called data mesh. It was introduced and invented by Jean-Marc Dehany. And data mesh comes with the same motivation to exclude monoliths, monolithic architectures, to avoid tightly coupled logic, so provide advices how to avoid it. And Mark Twain could say that, building monoliths, there is nothing more easier. I did it 1,000 times. And I'm sure a lot of us did it as well. It's the same problem as backend world faced as well. Let me tell you 4 big data temptations connected to monolithic architecture, of course. The first temptation is to build a monolithic pipeline when you combine all stages together, like ingestion, processing, transformation, validation, and maybe replication into one single job, one application. It might be natural for some decisions, for some architectures, but it's monolith, and it's bad in many cases. The second temptation is to put all pipelines into one application. I saw these applications. Sometimes they might have certain advantages on early stages, but in the end, they are monolithic and they slow down the first development and scalability. The third temptation is about more sophisticated monoliths. You might build pipelines quite nicely designed. Every pipeline is like sense of art, but together they are chaotically designed and inputs chaotically connected to the outputs of other jobs and pipelines, and you will have a mess at the end. So yes, individually pipelines are good, but together they produce chaotic, highly coupled pipelines, hell. The same problem, by the way, connected to microservices. If you have tens of microservices and you don't apply any layering and tiering, you'll have the same mess. You'll have the same monolith, just on higher level. And we are vulnerable here as well, big data. And the fourth temptation is to build monoliths inside data. It's quite easy to build tables with data and columns from different domains, which will be, because of that, slow, of course. And that's another type of monoliths. We also need to avoid it. All right, and if you have a lot of pipelines, if you have a lot of tables, it's quite easy to fall into a situation when you have monolithic architecture. And that's why, and that's where data mesh comes. So data mesh, as well as domain-driven design, means introducing bounded contexts for every subdomain. Every bounded context has, in in case of big data, must have own processing layer, own pipelines, and own organization decisions to serve exactly these domain needs. That's quite natural. That's how complexity might be split. And every subdomain should be owned by a dedicated team. Again, it might be that cross-functional team or, like assembled in different manner. But the point is that a team should be owner of these decisions made within this domain, and that's an important point for data mesh, like imposed to follow this practice. Data as a product means specific stance to data. It means that instead of just be an engineer who are owning the infrastructure and service, you are owning the product line and you productize your service. It's just another sense, like it's closer to product managers. And the data mesh imposes everybody to be a little bit product manager. And self-serving data platform. Well, if we allow our teams to build a lot of own small, tiny data pipelines and data platforms, at the end, you'll have a lot of boilerplate code and so on. So you need kind of foundational tier, which will absorb these duplications, these frameworks, libraries, which likely can be invented by all the teams. And likely, this tier might be isolated and even owned by a dedicated platform team. That's sometimes big companies have dedicated teams for this kind of work. And federated computational governance. What does it mean? Well, the same problem. Of course, every team must have ability and freedom to make decisions what kind of resources to allocate. I mean, AWS resources, cloud resources, and so on. And they should make decisions on it. But again, if I let everybody to make the decisions, you might have a chaotic infrastructure at the end with no rules at all. And you might face a lot of issues, security as well. And the only one way to avoid is to introduce like certain unified computational tier. And like teams will be allocating resources from the tier and using on own needs. That's how it might work, and data mesh imposes us to do it. So data mesh is, I must admit, quite good direction nowadays, and more companies adopt it towards own needs. Another trend is ELT over ETL. Let me explain first of all what ETL means. It's an acronym which means extract, transform, load. So your transformation pipeline should include 3 stages. First of all, you extract data or ingest from the data source. Then you transform it, maybe persist in intermediate storage data lake. And then you load data to your data warehouse, which is fine. And that's how things went for a long time. And even those Lambda architecture and so on, they like follow this practice, to be honest. It's a good approach. But the problem, before I tell you a problem, let me say good sides of it. First of all, it's quite scalable. It gives you a way to separate concerns. You can, for instance, involve technologies for transformation, unique technologies, unique clusters, which will be able to process amount of data. At the same time, you can involve different technologies for storage, and you can involve different technologies for extraction, and scale them separately, and make them available depending on your needs. That's a good side of ETL. The downside is that it takes certain time to let data be available inside data warehouse. Data must flow all the pipeline till the moment it is available. So increased data latency. At the same time, maintenance, it's quite high because of different technologies and different clusters involved. And if you would like to add something new, a new table and so on, you need to add all the tiers, all the components on this pipeline. Sometimes it slows down things. So cost of change might be higher, and adding new features, cost of change, and introducing new features also might be quite higher. And again, nothing wrong with ETL. It's just a good approach, but there is an opposition called ELT. It's also acronym. Its acronym means the difference actually is that transformation is moved to the last stage. And first of all, you need to extract data and flow to data warehouse as early as possible. And let data settle down in warehouse, maybe in raw format and accessible for end users, maybe. And then you can transform data if you need. By transformation here, we mean, like, first of all, we transform data with like leveraging database capabilities. It's important. A lot of us familiar with select insert SQL statements. That's about it. Also, there are ways to transform data through materialized views, any abstractions that help you to adjust data representation. So all this about transformation and can be involved. And the good side of ELT is that you reduce number of technologies, you leverage database hugely here, and you exclude some complexity because of that. And data latency is smaller because of that. That's a good side. ELT wasn't popular for a long time because, well, this approach existed for decades. But the problem was that back then it used databases, old-fashioned databases, which are unscalable. And those databases, they usually don't like when you at the same time put data and query data. It's like not good scenarios. They might be struggle because of concurrency issues and so on. And that's why it wasn't so popular. And today we have new generation of databases, MySQL, Snowflake, BigQuery, which are designed with different ideas. They have different DNA, and they are able to ingest data with no, like in isolation with querying data, with no issues to let them be doing efficiently. And that's why ELT was unlocked. And to be honest, it's very, very decent approach, very good approach. Nowadays, it's getting more popular, particularly on very beginning of the project. It might like speed up development. Later on, if you see that you need more solid processing, you involve a lot of pre-processing, you might move ELT and convert it to ETL. Sometimes I must admit that differences between ELT and ETL might be quite vague and obscure. For instance, you might introduce ELT, and you have several intermediate stages, and you flow, like, let data flow from one table to another with help of database. And yes, it's still like ELT, but it looks like ETL because data is still unavailable, and they will be available only when they come to the last table. So from this perspective, it's like not clear. We can call it ETL like ELT or ETL like ETL. ELT like ETL, yeah. So, you know, there are a couple of things we need to keep it in mind. But again, ELT is getting more and more popular nowadays, and those databases like Snowflake, BigQuery, they unlocked using this pattern in practice. Next trend is about technologies. The world tried to run away from SQL for 30 years, and turns out that it comes to the SQL again. There is a famous joke about democracy, so rephrasing it, it sounds like SQL is the worst query language, but others are even worse. And the trend is quite clear. SQL is appearing on many, many tiers. And a lot of companies use it as domain-specific language for a lot of tiers. And for instance, so SQL is not only about databases, as it was before. SQL is used for data transformation. SQL is used for data governance. For instance, those cleanup rules can be expressed with SQL, with predicate from SQL, and so on. It's about storage, and it's about data visualization. Data visualization also relies on SQL a lot. So SQL is I must admit that world still uses SQL and will for sure. And on developer level, I must admit there is also a trend that developers also leverage power of SQL and tend to build architectures and processing frameworks in a manner that they build a framework where SQL is also a DSL, and business logic will be expressed on SQL. So it's split on two stages. First stage is quite exciting for development because you are playing with interesting technologies, you're building great things. You have a lot of challenges, but once it's done, the boring stage comes when you need to implement business logic on pure SQL. But again, it might look worse, but From a business perspective, it's a good approach. It allows you to speed up delivery of new business features. And a lot of engineers adopt this practice. Somebody might think that SQL is like not good language, and you might build very ugly queries. But again, it's the responsibility of engineer. You can build heaven or you can build hell, completely driven by SQL. It's like not a problem of SQL. SQL has enough capabilities to give engineers chances to build nice and well, I would say, coupled SQL queries. It's a matter of you if you are not aware of them, if you involve them, or you just combine all nested queries together and produce this ugly thing. Another trend is about serverless. So as mentioned, we have serverless technologies, and looks like this serverless comes through all tiers. We have serverless technologies on transformation. We have serverless technologies on storage. We have serverless available on data governance and data analytics. And looks like you can build data platform based on completely serverless technologies. And in many cases, you don't need to provision your own infrastructure. You can just borrow some inside AWS, maybe inside subject domain technologies and so on. And it's good. It's good for sure. I'm not saying it will be cheap at the end, but for sure you will have shorter time to market for your solution. You might have less maintenance because you leverage cloud provider here a lot. You move the responsibility for infrastructure on his shoulders. In many cases, it works. At least it works most of the time. Even AWS falls down once per year, but still much rarely than our own solutions developed by pure developers. So here, definitely, serverless is a good sign. And a lot of engineers use it, with no exception. All right, let's talk about maturity. Here's the landscape of big data technologies for the previous year. And it's still incomplete. And big data went long way. And important milestone achieved, I must admit. Like engineering communities invented hundreds of ideas and converted them to hundreds of technologies, because behind each of these technologies is a brilliant idea. And the important milestone is that they are stable enough to be used in production and in conjunction to each other. It's really great to have stable tools, and in big data, we already have it. The another important sign on trend is mindset shift from the knowing specific programming language and technology to knowing something more and caring about other practices. It's like certain disciplines. It's mostly about data excellence. And a good data engineer, it's not enough nowadays to know only Spark, for instance, or Python and Scala. You need to know something more. And that something more is about data governance as well. You can address it as a checklist, and data platform must be addressed as a complete only if engineers address and cover all items from the checklist. Of course, there might be work items and items that are irrelevant for your case, but better to confirm and exclude it intentionally rather than just forget about it and found out about it later. And for instance, if you have a transformation layer to develop and you develop it, you must think about the data monitoring. The fact that data might be delayed, and you need to measure data delays from very beginning. It should be part of your monitoring and should be part of your transformation tier. If you address and need to, for instance, transform data, validate data, and replicate data, very likely you need to care about data quality, because you might see errors, you might see validation errors, you might see replication issues, and need to measure it. And if you have tables, very likely that you need to think about retention policy. A few engineers think about it, to be honest, but that's the important part. We pay for tables, we pay for costs, even if it is S3, sometimes cost and figure of data, footprint of data might be quite sensitive, even on S3. So that should be centralized strategy, and we need to think about it in advance. And good data engineer is an engineer who think about this checklist in advance and ask this question from very beginning. All right. Do you know what it is? This little thing made a revolution in 1970s. And most of innovations we have now happened because of this first microprocessor invented by Intel company. And back then, Intel wasn't a product company. This company was a hardware development company who made each hardware as a service for every new customer from scratch. And one day they realized that they spent a lot of time doing it from scratch again and again. And they realized that they could introduce a kind of usable component and microprocessor and speed up delivery at the end. That's how this first 4004 appeared. And I'm telling you this because we are seeing the same trend in data engineering. A lot of companies realized that specific problems exist, and they invented kind of microprocessor for these problems. And that's another trend, productizing big data. So a lot of companies accumulated a good practice how to build data platform, and they, as mentioned, realized so there is a problem to build, for instance, data lakes, there is a problem to build data warehouses, there is a problem to build processing ETL, and they try to provide well-tailored solution to solve exactly this problem and automate as much as possible. And there are many examples. Let me focus on particular one, the technology called Absolver. Technology Absolver, it's interesting technology, by the way. So guys from Absolver, they thought, what if we build technology which will be a microprocessor for data platforms? So they produced a service which I could call as a data platform as a service, something like that. Completely managed serverless approach, and you can use it to build your own data platform. You can use like drag and drop and compose your processing, storing. You can make decisions very easily, and everything will be automated and done by Absolver. And at the end, you can build your data platform within minutes or even hours or maybe days if it's quite complex. Of course, it has certain limitations. For instance, SQL-driven transformation should be supported. Of course, if you need something more, they support UDF, but UDF may be not good if you have indeed complex and huge logic there. However, there are a lot of customers who need exactly this. They don't want to spend saying months trying to build something driven by Spark or Presto. They just want something that will be working for them tomorrow. That Absolver is a really cool technology. And the last section today is innovations. The first is data warehouses. I already mentioned about data warehouses. It's really cool trend, and data warehouses helped to rethink understanding of what data lake and data warehouse is. As mentioned, data lake likes regular ingestion and regular processing. It doesn't like random low latency queries that might come to the data lake. At the same time, data warehouse likes low latency queries and don't like real-time ingestion. And smart guys thought, what if we can combine both technologies and find a way how to implement it? And they found. In most cases, these technologies separate storage and computational tier in completely different layers. Storage usually is based on pure S3. It's insane, but they leverage the strong side of S3 and weak side to write and read data from S3 directly in consistent way with no dirty writes and dirty reads. That's amazing. And in fact, there were two generations. Of course, it's it's conditional separation. First generation, it's about Iceberg, Data Lake, and Hoodie technologies that they provided. Well, they were first, I would say, and they provided rather than it's not databases. They are rather client-side APIs. And you can use them, but you need to provide your computational tier. You need to provide your cluster, allocate your resources. You need to involve your framework, for instance, Spark, which will be using this API to connect this data. And in most cases, it's enough. For many projects, these third-generation tools, it's enough. These technologies are alive nowadays. However, there is a second generation of tools. Some companies thought, OK, what if we, based on that and those brilliant ideas, add some computational tier, some enterprise support, and build complete databases out of the box. And they made it with Snowflake, Dreamio, and others. So the second generation of tools, they are databases based on this technology. So they use S3 as a storage and computational tier to run your queries. And they do this magic to separating concerns and so on. And for instance, if we talk about Snowflake, I could tell killer feature here. What about time? Oh, time is running out. So the killer feature of Snowflake is that they involve data warehouses on demand. So the unit of computational logic is warehouse. And you can create as many as you need them. They are completely stateless. You can specify this warehouse should have 8 cores. This warehouse should have, for instance, 16 cores. And you create as many as you need. You can scale it down, scale it out, stop within seconds, create within seconds. They support auto-scalability, by the way, and auto-suspend and auto-resume. And it gives you a chance for regular developers. It means that you can spread your workload into these warehouses. And that's why you can implement ELT based on Snowflake. You can have one warehouse for ELT or ETL. You have another warehouse for low latency queries. You have another warehouse for machine learning and other stuff. And that unlocks you on doing a lot of different new patterns which are completely hidden and unavailable on traditional databases. I'm not saying Redshift is bad, but Redshift is a monolith. You have everything inside tightly connected to each other. State, cache, storage, and computational resources. You can scale it out and scale it in seconds. With Snowflake, you can. So it's amazing technology. All right, let me speed up. So rise of business intelligence, that's the last trend for today. Again, as mentioned, the trend is serverless. And we've seen the same pattern on BI tools. BI tools, in a nutshell, it's tools which gives users a way to play with data, build funny and fancy dashboards. And of course, it's like playground for data. And for a long time, BI was an on-premise solution. And you have to have a Devoxx who knows how to install it, like Table and so on. But nowadays, we have a different trend, and a lot of these BI tools are serverless and more than SaaS in a model like pay-as-you-go. In most cases, it's like pay-as-you-go or credit model, very close to it. So it's clear that you can, instead of deploying it and configuring it, you can just borrow license and play with it and pay only for uptime. The same as Snowflake, by the way. So that's a clear trend nowadays. And most of these tools support ELT. It's a kind of simulation of data platform. If you don't want to invest a lot of time and money for your own data platform, you can build these abstractions and some tiny transformation on top of your BI tool. And it works. On the beginning, it might be a very good alternative, by the way. But you need to be brave enough to stop one day if you notice that, for instance, response time is higher, or you spent more, your monthly bill was increased. It's clearly signs that you need to change the paradigm. And probably it's time to introduce solid data platform instead of having this simulation. And also these new BI tools, they like self-service, like the single BI tool for organization, and every department might adjust it over its own needs and so on. And the last cool feature, again, dangerous but cool feature. These tools allow you to query data not from different databases, from different cloud providers. For instance, you might query data from BigQuery and from Snowflake. There are startups who might have a major data lake in AWS. At the same time, they add tech startups, for instance, and they use BigQuery because they use GAM, Google Ad Manager. So maybe at the beginning, easier to join data within the BI and not building something complex. And hybrid sources, that's another cool trend. And on the beginning of, like on early stages, it might be completely justified to use this feature to build data platforms. All right. That's it for today. Thank you very much. If you have questions, I will be glad to answer.